to our operational research class module. On this module, we'll be looking at scheduling. Remember, in our previous study, we just exclusively with the transportation problem, and then we look at the consider network analysis. There it is shown that the map of route between nodes is called network. But in this chapter, or in this module, we shall consider three types of problems that involve in route scheduling. And those problems are the minimal spanning tree, minimal spanning tree. Then secondly, we'll deal with shortest path. Then thirdly, we'll consider circular tour of all nodes. Circular tour of all nodes. To start with, minimal spanning tree. Now the minimal spanning tree, the problem we are trying to solve is a very straightforward way of analyzing network. That is, we minimize the cost in network analysis. We have different algorithms in solving the problem. The first algorithm looks this way. When you have a map, this is a network map, the map of a network. You have A, B, this position C, and this position D. We have another network here, position E. We have position F, and we have position G. All these routes or positions are linked together in this way. All these links, they all have different measurements, all in meters. For instance, position A to B, let's assume it is 1 meter. Position A to B, 2 meters. Position A to C, 4 meters. Position C to D, 4 meters. Position C to G, 3 meters. Position D to F, 10 meters. Position D, let's see, position D to E, 7 meters. Position B to D, 1 meter. Position A to E, 10 meters as well. Position E to G, 5 meters. Position E to F, 8 meters. Position F to G, 3 meters. On this spanning tree, we want to reduce the numbers. Let's assume all these are cables of different meters. We want to reduce the number of cables that is being used in this network. So what do we do? According to this algorithm, what we do, we start. Let's assume our point A is the starting point. Point A. We consider all the nodes that are connected to point A. B is connected to A, C is connected to A, and D is connected to A likewise. From A, the shortest distance that is connected to A is D. So we move to D from A, that is 1 meter. D. When you consider from point C, point B is connected to D, E is connected to D, likewise C and F. We consider the shortest distance. The shortest distance so far is point D, so we come to point D from D. That is 1 meter. If we should move back to point A, being the other point that is connected to B, we will be making a mistake in our network because we will be having, there is no way we will be able to get to our destination point, that is point G. So from point G, we come back again to point C. Mind you, this point is still a valid point on the network. So we have 4 meters, being the next shortest distance from point D. Now, we consider other points. When we look at consider the point connected to C, we have point A, which we can go back to, and we have point G. And point G is 3 meters, so we come to point G from our point C. G. That's 3 meters. 3 meters. From point G, we consider another shortest point. Point G, F is connected to it, likewise E. The shortest point from point G is point F, so we come to point F. That's 3 meters as well. When you look at the network, you will notice that we'll be able to move from point A to B to C. We've covered C, we've covered D, we've covered F and G. The remaining point is point E. When we look at the nodes or the points that are connected to E, we have 8 meters and 5 meters. The shortest from it is 5 meters, that is coming from point G. So the next connection we'll be making will still come from point G to E. That is 5 meters. That's the minimal spanning tree. Spanning tree of this network. At the end of the day, we consider the distance covered so far compared to what we have initially on the network here. From A to G is 1 meter. From D to B is another 1 meter. From D to C is 4 meters. From C to G, we have 3 meters. From G to F, we have 3 meters, and from G to E as well, we have 5 meters. When we add everything together, 1, 2, 6, 9, 12, 17. Everything all together gives us 17 meters. Compared to what we have initially there, when we compare the two networks together, we know that with this, we've been able to economize everything that's needed to start to move through the network. There are 2 other problems that we can use this to solve. We will consider them in the next module. Thank you.